Good morning. Today we will study about conductometric titrations. You have earlier studied volumetric titrations in your BSc second year, volumetric titrations. What are the advantages of conductometric titrations? Because of several advantages, conductometric titrations are very much used in industry, especially in industry. What are the applications? Colored solutions can be titrated, whereas in volumetric titration, volumetric method, the colored solutions cannot be titrated because in volumetric titration, the end point is the change of color. Therefore, colored solutions cannot be titrated in volumetric methods. Next, dilute solutions can be titrated. Even small concentrations can be determined by using conductometric titration method. And third point, there is no need to take special care near the end point, because the end point is determined from the graph, from the conductometric titration graph. Okay, therefore, at the end point, for example, in volumetric method, the end point is very, very important. At the end point, there is a color change, there is a sharp change in color. So, if you add excess volume, then the titration, you need to repeat the titration. But here, it is not required because there is no need to take special care near the end point. Okay, we will see further why it is so. Now, how do you define conductometric titration? Define conductometric titration. Here, the conductance is measured as a function of volume of titrant added. Okay. The conductance is measured in conductometric titration. The conductance is measured as a function of volume of titrant added. In potentiometric titration, the potential is measured as a function of volume of titrant added. Okay. So, now this is the setup for conductometric titration. This is the setup used for conductometric titration. For example, you have a beaker. In beaker, you can take HCl, hydrochloric acid, and burette, nitroburette. You can take alkali, sodium hydroxide. Okay, acid-base titration. This is a conductivity cell. We have seen in the previous class. A conductivity cell is immersed in the HCl solution. A glass rod is used to stir to homogenize the solution. Okay. Now, let us see. There are 5 types of conductometric titration curves. In this class, we are going to see. One is strong acid versus strong base, weak acid versus strong base again, and third, a mixture of strong acid, weak acid versus strong base, and fourth is strong acid versus weak base, and fifth one is precipitation titration curve. Okay, now let us see strong acid versus strong base, HCl versus sodium hydroxide. HCl is taken in beaker, sodium hydroxide is taken in nitroburette. In the beginning, T equal to 0 means in the beginning the conductance is high. Why the conductance is high? You are having only HCl. You are not added alkali. Therefore, H plus Cl minus. See, remember H plus Cl minus. The H plus ion is highly conducting. The conductance is high because of highly conducting, high mobility, due to high mobility of H plus ion. Okay, therefore it is high, very high. See, and on adding alkali, Na plus OH minus. This is initial Na plus OH minus. Therefore, H plus OH minus is water and Na plus Cl minus, and Cl minus is there. We can cancel it. Therefore, H plus is replaced by sodium ion. Sodium ion is poorly conducting. Remember, so H plus ion is highly conducting, is replaced by poorly conducting sodium ion. Therefore, the conductance sharply decreases. The conductance decreases until the end point. Conductance decreases until the end point. Further addition of alkali beyond the end point, the conductance increases due to the excess OH minus ion present in the solution, because all HCl is neutralized. Therefore, excess in OH minus ion increases the conductance. Okay. Now, what is conductance depends on 2 factors. Remember, conductance depends on 2 factors. Mobility of the ion. mobility of the ion, and the number of ions. Number of ions, for example, H plus number of ions is high, therefore conductivity is high, and the conductance decreases because the number decreases, and also mobility of sodium ion is less compared to H plus ion. Okay, the end point, now the end point is determined from the intersection. End point is the intersection point of two straight lines. The point of intersection gives the end point. The end point is the volume of alkali. This is the volume of alkali required for complete neutralization of HCl. Volume of alkali required for complete neutralization of acid. Okay. Next, let us see weak acid versus strong base. Weak acid versus strong base. Now, in beaker, we have taken weak acid, acetic acid. For example, acetic acid versus sodium. Acetic acid we have taken. Acetic acid is, in the beginning, the conductance is low. See, the conductance is high in the case of strong acid. In the case of weak acid, the conductance is low because of weak acid taken in the beaker. Therefore, why the conductance is low? Due to partial dissociation or partial ionization or incomplete dissociation. Okay. Further, on adding alkali, similarly, on adding alkali, the conductance slightly increases. The conductance slightly increases because this is acetic acid in the beginning, and then on adding alkali, Na plus OH minus ion, and it forms water neutralization because of neutralization reaction H plus water, and the acetic acid is replaced by sodium acetate. Acetic acid is replaced by sodium acetate. Therefore, acetic acid is not conducting. Not conducting because it is not dissociated. It is undissociated. Whereas this is conducting. Sodium acetate. Acetate ion is conducting. Therefore, there is a slight increase in conductance because of the acetic acid is here. Acetic acid is replaced by acetate ion or sodium acetate. Okay, because of ionized sodium acetate formed. And further, the third and fourth points are said. Further addition, so it increases slightly until end point. Until end point. After the end point, further addition of alkali beyond the end point, the conductance increases similar to this. The conductance increases because of the excess of OH minus ion, because of the introduction of excess of OH minus ion in the beaker, in the solution. Okay. Okay, now the point of intersection. Similarly, the point of intersection of two straight lines gives the end point. Same as this. Right. Because next, third one, we are taking 20 ml of HCl and 20 ml of acetic acid, strong acid, weak acid. A mixture of strong acid, weak acid, and titrated against same sodium hydroxide alkali. Now, the titration curve for the mixture is shown here. It is a combination of these two curves. For example, this decreases, and then this, and then this. It is a combination of titration curves 1 and 2. Okay. In this case, HCl is the strong acid is first reactant, reacting, and first titrated, and then the weak acid is titrated and is reacting. Why HCl? HCl is a very strong acid, therefore it reacts first, therefore it is titrated first, and this is the end point for volume of alkali required for complete neutralization of HCl, and this is the volume. This V2 minus V. This is the volume. This volume is required for the complete neutralization of the weak acid. Okay. Next we will see strong acid versus weak base. Strong acid versus weak base. Okay. Now conductance versus volume of ammonium hydroxide added. Now you take HCl here, ammonium hydroxide instead of alkali. Ammonium hydroxide is taken in the microburnette. Okay. Now you see HCl. HCl is taken in the beaker. Therefore, the conductance is high. Similarly, in the beginning, the conductance is high because of highly conducting H plus ion. And adding See H plus and Cl minus in the beginning. Then on adding ammonium hydroxide, the reaction takes place. Neutralization reaction takes place. Now H plus ion is replaced by ammonium ion. Remember, H plus ion is replaced by sodium ion. H plus ion is replaced by ammonium ion. Ammonium ion is poorly conducting. Similarly, sodium ion, Na plus ion, ammonium ion is also poorly conducting. Therefore, there is a sharp decrease in conductance. Okay, until the end point. After the end point, the ammonium hydroxide is added excess. See, ammonium beyond the end point, the conductance remains. There is no change in conductance because of addition of ammonium hydroxide, which is undissociated, which is not dissociated, only very weakly dissociated. Okay, therefore there is no change in conductance after the end point. They will ask why there is no change in conductance after the end point, because of the excess of ammonium hydroxide, which is undissociated, which is only partially dissociated. Let us now see precipitation titration. Precipitation titration can also be carried out by conductometric titration method. For example, silver nitrate is taken in beaker, potassium chloride is taken in microburette. This is the titration curve for precipitation reaction. Ag plus in the beginning, similarly in the beginning Ag plus NO3 minus, the conductance is low because it is H plus only highly conducting, it will be low, and Ag plus on adding alkali, on adding KCl, conductance here on adding K plus Cl minus, precipitation takes place. AgCl precipitate is formed plus K plus NO3 minus. Therefore, Ag plus ion is replaced by, see, you write similarly, Ag plus ion is replaced by K plus ion. Therefore, see, the mobilities of silver ion, the mobility, U means mobilities of the silver ion and the potassium ion are similar. Therefore, there is no change in, see, Ag plus, there is no change in conductance. Why? Because the mobilities of the silver ion and the K plus ion, therefore the conductance are almost equal. Therefore, there is no change, appreciable change in the conductance up to end point. After the end point, K plus ion, see, further addition beyond the end point, the conductance increases because of the K plus and Cl minus ion, because of the excess addition of K plus and Cl minus ion. Okay, so the end point is now determined from the point of intersection. Therefore, the normality, the concentration of either silver nitrate or potassium chloride can be determined. Okay, now there is one factor, very important factor, I will tell you, effect of dilution. For example, when you add alkali or when you add potassium chloride, what will happen? There is increase in volume. See, there is increase in volume. There is effect of dilution. There is dilution factor. There is the effect of increase in volume. This also decreases the conductance. See, because of dilution, the conductance decreases, and also because of removal of H plus, the conductance decreases. Therefore, we will see in the following.
What is the effect of dilution on the conductance? For example, when you add alkali to acid taken in the beaker, there is an increase in volume, there is an increase in dilution. The conductance decreases also due to the effect of volume, due to the effect of dilution. So, in the titration curve, a straight line is not obtained. A straight line is obtained here, but a straight line is not obtained. Instead, a curve is obtained. Because of the effect of dilution, effect of volume, to account for this effect of dilution, the volume correction factor B plus B prime divided by B where V equal to initial volume acid taken, for example, V prime is the volume of alkali added during the titration, is multiplied by the volume correction factor is multiplied by the measured conductance in y-axis. After the volume correction, a straight line plot is obtained like this. Otherwise, if you plot conductance versus volume of alkali due to dilution effect of volume, as I said, the conductance decreases. Therefore, the straight line is not obtained. Okay, after the volume correction in y-axis, the straight line plot is obtained. Further, to decrease the effect of volume dilution, the titrant in burette, the titrant taken in burette is always 5 to 10 times more concentrated than the solution taken in the beaker. Remember, in order to eliminate or decrease the effect of dilution, the titrant is always 5 to 10 times more concentrated than the solution taken in the beaker. Okay.